Hi everybody. Whenever you add or subtract, you have to make sure that the objects you're adding or subtracting are of the same type. So this is a concept which cuts across a lot of areas of math that you may be learning about. So this is true whether you're adding or subtracting fractions or decimals, or you're combining like terms, which is adding or subtracting algebraic terms together. This is true if you're adding or subtracting numbers written in scientific notation. So this is a concept which cuts across anything that you might be adding or subtracting. You must make sure that the objects which you're adding, which is putting together, or subtracting, taking away from each other, are of the same type. So let's look at a very simple example that we might see in elementary school. 3 apples plus 2 apples equals 5 apples. That makes perfect sense because I'm adding objects which are of the same type. I'm adding objects which are both apples. 3 bananas plus 2 bananas equals 5 bananas. Again, no problem. It makes perfect sense. But what if we have 3 apples plus 2 bananas equals 5 apples? No. If you have 3 apples and then somebody gives you 2 bananas, you don't all of a sudden have 5 apples. So that doesn't work. Why didn't it work? Because we were trying to add objects which were of a different type. So we were adding apples here to bananas over here. It just doesn't work. Now you might try to be clever about it and say 3 apples plus 2 bananas equals 5 apple bananas. Nice try. No. Again, that still just didn't make sense. If you have 3 apples and somebody gives you 2 bananas, you don't have 5 apple bananas, whatever those are. So again, you have to be adding things which are of the same type. And you could say the exact same thing for subtraction. If you have 5 apples, you can't take away 2 bananas, right? Again, it doesn't make sense. So that's one example. It's the exact same idea if we're combining like terms. So here we have 3x plus 2x equals 5x. And very often people will represent an x as just a long thin bar. Okay, so this makes perfect sense over here. 3 bars plus 2 bars is equal to 5 bars. No problem. If we have 3x squared, so sometimes people represent x squared as literally squares, which makes sense, of course, because x times x, which is x to the second power, is how you would calculate the area of a square where each side was x units long. You would do the length times the width, which would be x times x. So that would give you the area of a square, again, where each side is x units long. So it makes sense mathematically, but I went through that quickly. If that confused you, then just focus on the pictures and it's fine. So 3x squared plus 2x squared equals 5x squared. That makes sense from these pictures because if I have 3 squares and I add 2 more squares, then I have 5 squares. Fine, right? No problem. But this one over here, if we try doing 3x plus 2x squared, so we're adding 3 bars to 2 squares, we do not end up with 5 squares. So this over here, 3x plus 2x squared equals 5x squared, this does not make sense. And the reason it doesn't make sense is because we tried adding objects together which were not of the same type. These were x's over here, and these were x squareds. Okay? So it doesn't work. And you can say the same thing about adding or subtracting. I'm doing a lot of addition examples here because They're just easier to represent with drawings, but you could say the exact same thing for subtraction. So in elementary school, your teacher told you to always line up the decimal when you're doing addition or subtraction, right? Do you remember why that is? Why do you always have to line up the decimal if you're adding or subtracting? Why do you always have to line up the decimal point if you're adding or subtracting decimal numbers? Why was your teacher so strict about that and didn't just let you do it with the decimal points not lined up, which would have been so much easier for you, right? Well, because it's only when you add up the decimal point that you're adding or subtracting like objects, okay? If the decimal point is not lined up, then it's just like you're trying to add apples and bananas. So let me tell you what I mean by that. So remember, the decimal point is what we need to look at to determine place value. So something just to the right of the decimal point, that is the tens place. And then the next one over is that is the tenths place. And the next one over is the hundredths place. Okay, so you know what? I'll do this. Let me do a little drawing of it. Okay. All right. And then to the left of the decimal point would be the ones place. And then again to the left would be the tens place. So imagine 5 tens. Imagine a 10 is something which is relatively big, okay? Let's say that that's a 10. So this is telling me that I have 5 of these things, which are relatively big. And then I have 3 ones, and let's say that a 1, it should be 10 times smaller than a 10. Okay, let's say that that is a 1. Okay, so this is telling me that I have 5 of these 10s and 3 of these 1s. And then this one over here is in the tenths place. So a tenth is really small. I can't even fit the number in there to say that that's a tenth. But that would be 10 times, I know I'm not drawing all of these very well, but this would be 10 times smaller than a 1, and a 1 is 10 times smaller than a 10. And then we have this place, which is the hundredths, and that's what we'll do for the hundredths. So a hundredth would be 10 times smaller than a tenth, which is 10 times smaller than a 1, which is 10 times smaller than a 10. So when the decimal points are lined up, then we're adding like objects together. We're adding objects which are of the same type. So for instance, I'm adding 1/10 to 5/10. So that 1/10 means 1 of these guys, 5/10 means 5 of these guys, and when I add 1/10 plus 5/10, I get 6/10, which is 6 of these guys. So that makes sense. And when I add 3 ones, remember this 3 is in the ones place. When I add 3 ones plus another 6 ones, we can see that both of these digits are in the ones place because they're both one space to the left of the decimal point. So 3 ones plus 6 ones equals 9 ones. And I know that that 9 is in the ones place because that is also just to the left of the decimal point. So when I have the decimal point all the decimal points lined up, then all of my answers make sense. I'm adding hundredths to hundredths, even though I didn't actually have any hundredths in this example. I'm adding tenths to tenths. I'm adding ones to ones and tens to tens, even though I didn't have any tens in this example, and so on and so forth. I would be adding hundreds to hundreds, thousands to thousands, and so on and so forth. But if I do not have the decimal points lined up, then look at what's happening. This is in the tenths column. But this 6 over here is now to the left of the decimal point, so this 6 is in the ones place, or the ones column, it's sometimes called. So what I'm doing here is I'm trying to add 1/10, so one of these guys, to 6 ones. So one of these guys plus 6 of these guys does not equal 7. You can see that this 7 is in the tenths place, but adding 1/10 to 6 ones does not give me 7/10. Okay, so adding one of these to 6 of these does not give me 7 of these. All right, and look over here, we have 2, but that 2, since it's 2 places over from the decimal, is in the hundredths place. And this 5 is only 1 place over from the decimal, so this is in the tenths place. So what we're doing here is we're trying to add 2 hundredths to 5 tenths. That means and then this 7 is in the hundredths place. So what we're trying to say, or if if somebody writes this, then what they're trying to say is that 2 of these little guys, these little tiny ones, those are the hundredths. 2 of these hundredths plus 5 of these tenths is equal to 7 of these hundredths. Again, it doesn't make sense because we're trying to add things which are of a different type. And the last example that I'll go over here is with fractions. 3/4 plus 2/4 equals 5/4. This makes perfect sense. What is a fourth? Well, think of a pizza pie, which is split up into 4 equal pieces, 1, 2, 3, 4, and then we have 3 slices, 1, 2, 3, so that's what 3/4 is. So 3/4 plus 2/4 is equal to 5/4. If I eat 3 slices and then you eat 2 slices, altogether we ate 5 slices, okay? Where each slice is a fourth of the pizza pie. So this drawing over here makes perfect sense. But you can't add fractions where the denominators are different, and that's a rule that your teachers probably told you over and over and over again, but you might have forgotten why that is. But the reason why it is because it just doesn't make sense. If I have 3/4, which is this picture over here, it's a pizza pie split up into 4 equal pieces, and then I add 2/8, which is 2 parts of a pizza pie, which is split up into 8, 1, 2, 3, 4, 5, 6, 7, 8 equal pieces, that does not equal 5/4, okay? Because, if you eat this much of a pizza plus this much of a pizza, then altogether you did not eat this much of a pizza, okay? Now, what you could say, though, is you could split this one up. Let me choose a different color here. You could split this one up so that this is also, I didn't do that very well, but let's just pretend that I did it well. And this is also split up into 8 equal pieces. So now we have 1, 2, 3, 4, 5, 6 pieces which are shaded in. So we could say that 3/4 is equal to 6/8. And we could say that 6/8 plus 2/8 is equal to 8/8. So now we have 1, 2, 3, 4, 5, 6, 7, 8. Whoop, and these are just gone, right? Oh, I didn't even, yeah, so this is just gone. I didn't even have to bother drawing the lines in there. Okay, so I have 1, 2, 3, 4, 5, 6, 7, 8. So that's the 6 plus 2 is equal to 1, 2, 3, 4, 5, 6, 7, 8. So this all makes sense when we're adding like objects. The objects in this case being eighths, right? I can add eighths to eighths. I can add fourths to fourths. but I can't add fourths to eighths, at least not easily, unless I change it so that the denominators are the same. Okay? So again, the idea is we always want to add or subtract objects which are of the same type.